Good morning. Our first speaker is Dr. Tom McAvoy. He received his BS in chemical engineering from Brooklyn Polytechnic Institute in 1961 and received his PhD in chemical engineering from Princeton University in 1964. He taught chemical engineering for 40 years, first at the University of Massachusetts and then at the University of Maryland. Tom is currently Professor Emeritus in the Chemical and Biomolecular Engineering Department at the University of Maryland. He has published over 200 scientific papers. These publications include 3 papers in refereed journals and 1 conference paper on his research on the ultraviolet-induced fluorescence images of the Shroud taken by STURP photographer Vern Miller. He is the author of the book God the Geometer. And let's welcome Dr. Tom McAvoy.
It's interesting, at the conference, 1 or 2 people saw the speaker sticker, and they asked me, "Oh, what are you talking on?" And I gave them the title of the talk, and they kind of looked like a little bit sideways, like, you know, why would you work on something like that? So that made me think it might be best to start out and tell you my conclusion, and then and then I'll go back and I'll give the talk. There are 2 parts of it. One is we really want to have more data on the Shroud. Everybody just about agrees to that, and unfortunately the authorities that would allow that don't allow taking additional data. The nice thing about the ultraviolet work that I've looked at is that the data comes from the Shroud. So this is actual Shroud data. And so that's one aspect of it. And and I'll remember what the other part was. I've forgotten it. But let me go on and start with the point of what is artificial intelligence and how does it work. AI uses data to learn and solve problems, and data is essential for training AI algorithms. Just last night I went on and I just Googled who coined the phrase AI, and John McCarthy's name came up, and it was in 1956, and right at the top it says AI generated. So all your Google searches now will say AI generated. And in a sense, AI is very similar to the Shroud. It may have been coined in 56, and then in the 70s, STURP took or made its scientific study of the Shroud. And both of these areas kind of lay dormant for a long time. I mean, people, worked on them in academia, or the syndenologists worked on them, but you didn't hear a lot about them in the public press and everything else. All of a sudden, in the last couple of years, they've both taken off. AI, is everybody's concerned about it, and they're using it, and what's it going to do? What are the negative effects? And the Shroud, in the last couple of years, the interest has gone up enormously. So they're very similar in that regard. So AI uses data, which is essential for training the algorithms. Now, I'm going to talk about one type of algorithm. And I retired in 2004. I had done work in the AI field in 1990. And I had not really kept up with the software since I retired. So I'm going to talk about commonly used statistical techniques, which is what we used when I was looking at applying neural network methods to chemical process systems. And we were also looking at using these statistical techniques like regression analysis, cluster analysis, classification, and then I want to specifically talk about a dimensionality reduction technique. And there are others, and there are many more that today people are using, so that when you get on Google and you Google for something, you get the answer from the AI expert at Google. So I'm going to focus on something called principal component analysis, which is a dimensionality reduction technique. And I'll explain what that is on the next slide. So here is principal component analysis. What you have is, with principal component analysis, and I'm going to use the acronym PCA for it, it sequentially calculates linear combinations of variables in a database that explain the maximum variance in the data. Now, it's the variance in your data in terms of the kind of application I've done that really contains the knowledge and the information, okay? So you're looking for trying to explain that. It uses linear algebra and matrix calculations. And I'm going to assume with this group that you're not particularly interested in linear algebra and matrix methods and eigenvalues and stuff like that. So this talk is going to have no equations, okay? And hopefully I can explain principal components to you in a way that doesn't require any equations. Now the Shroud has 3 variables. The Shroud photos, or the Shroud photos have 3 variables. And these are the magnitude, they're RGB photos, meaning red, green, and blue, okay? Even though they're ultraviolet photos, you have red pixels, green pixels, and blue pixels, and they're referred to as RGB images. So you have 3 independent variables. What's the magnitude of the green, what's the magnitude of the red, and what's the magnitude of the blue? For 3-dimensional databases, you can generate 3 principal components, PC1, PC2, and PC3. Now, the method, principal components, is an old method. It's probably close to 100 years old. So it really predates AI. One of the things we did in the research was we combined principal component ideas with neural networks, and we had something called principal curves, which allowed for nonlinear extensions of the method. It turns out for the Shroud, you really don't need anything more than principal component analysis. PCA has actually had tremendous benefits in the chemical process industries. I'll give you one example. First, let me describe it kind of generally. If you have a chemical plant and an operator is running the plant, the operator might sit in front of 30 or so different measurements that are displayed to them. So you'll see temperature, pressure, flow, stuff like that coming in. And what you'd like to know is there any problem developing in the plant? And the operator typically is not going to be able to look at 20 different things at once, or 30. It's just too many. So they would tend to discriminate and say, well, I'm going to, this is my favorite measurement, or this one is, or this one is. And it would be a lot better if you could take all the measurements and use them some way. And that's what principal components allows. What you can do is make a linear combination of the measurements that you have, and then display the linear combination to the operator. And you might have maybe 2 of these combinations that you really would like the operator to see. In the case of the chemical example, you would take your measurements when your process is running in a good way. You don't have any bad off-spec products coming out. You're happy with the way the process is running, so you collect the data and you make your model based on that data. And then what you'll look for is violations where all of a sudden the principal components start to deviate from what they had been when everything was okay. Now you need additional knowledge to say, well, what does that type of violation mean? All right. There are a lot of examples that people have published. Predictive maintenance is one, where you start looking at a bunch of variables and then you can make a prediction that, okay, we're going to need to replace that bearing because things look like they're starting to go bad. There was one example in Canada that involved pouring molten steel to make ingots. And they would run in, rarely, but it would happen, where there was some kind of a fault in the process, and now they'd be pouring molten steel over their equipment. And obviously that would cost a fortune. They'd have to shut everything down, clean the mess up, and restart. And they went to using something like principal components, and they were able to cut down the number of faults enormously by just compressing the data and then getting an alert early enough that they could actually stop the process before there was a disaster. So it's had all kinds of uses. Now for the shroud, with only 3 principal components, you don't need nonlinear PCA. And regular PCA still does a good job. It's going to compress the 3 components, as we'll see. So here are some ultraviolet photos of the shroud. And I don't know if Gil Lavoie is here. He's going to speak later. But these ultraviolet images here, this is one of them, were put on the web by Gil and Tom DeMulla in 2019. They were taken by STURP in 1978, and so it's 41 years after that that they became available to the public. And the original images were lost. So what Gil had was he had copies that were made of the original images, but they were made with something called color correction filters. So the colors were different and whatnot, and that caused some issues in terms of trying to get back towards the original images. And what you see here is what happens if you apply principal component analysis to the shroud, to this ultraviolet image. And you decompose it into 3 components. The first component, second, and third. And if you look, the first component captures the vast amount of information in that photo. In fact, I can use that first principal component, and effectively, if you look at that, you can hardly see any difference between that and this. So what you have now is, instead of dealing with red, green, and blue, I can deal with the first principal component, and that's all I need to know, and I can reconstruct the shroud image. And that happens for all of the ultraviolet images. Let me give you an example. These are referred to as orthogonal decompositions. And let's say that I have a point in space, and maybe the origin is over here at the dais, and you want to describe where the point is. Well, I can give you the x and the y and the z dimensions, and those are orthogonal to one another, perpendicular, and you can get the point. Now, another way to do that would be to take a curve or a straight line from the origin up close to the point. I don't want to go right through it, but it'll go very close to the point, and now I have that straight line. Then I put another straight line perpendicular to that one, and another one perpendicular to the third one. So I have 3 straight lines, but the last 2, well, if I want to know where the point is, all I really need to know is that first dimension. I'll get very close to where the point is, and that's what happens here, that if I know the first principal component, I effectively know what's in the ultraviolet photo of the shroud. And this happens for essentially all of the images that Vern Miller took. So that's a key result. And then the question that we have to figure out once we get this is, what does it mean? Okay? But now I don't have to deal with 3 dimensions, I can deal with 1. And I'll give you an example that is another photo. This is one I took in my backyard. We have had a bird feeder. It's hard to see, but this is a Baltimore Oriole. It has an orange breast and it likes to eat oranges. And this is the bird feeder. And so if you take this photo and you get the principal components, the first principal component only picks up 75% of the information in that image. And the second component picks up 19, so we're still missing about 6% of the information. And if I put all three together, this plus this plus this, I get the original image. But you don't need that with the shroud. And that's quite an advantage then in looking at principal components. So what we find is when we look at the ultraviolet images of the shroud, that PC1 for the shroud captures essentially all the information from the UV images. And now it can be shown, and I'm not going to go through this because it would require some equations, but PC1 is essentially equal to the intensity of each pixel, okay, in the UV image. So if you go over the UV image and you calculate the intensity at each pixel, all right, that is essentially equal or correlated essentially 100% to the first principal component. Whoops, wrong one here. And then the intensity, for purposes of this talk, is proportional to the sum of the red, green, and blue pixels. So you don't really need all the pixels, you just need to know the sum of the red, the green, and the blue. And if you know that, and you know the average value of the red, green, and blue, you can recreate the UV image. All right? Now, I probably should have worded this a little differently, but it says, importantly, the shroud UV image intensity. I should say the shroud UV image reflects the molecular properties of the shroud, which are discussed in the next slide. And since the image intensity is essentially equal to the image, it's the image intensity also reflects then the molecular properties of the shroud. Okay? And molecular properties would include things like, one of the things we're interested in is the molecular bonding in the linen. Okay? But the shroud it's got water stains, probably some other kinds of stains on there. It's got burn marks, it's got blood marks. So contamination is also going to be picked up by the ultraviolet images. Okay. So let's see how we would do ultraviolet photography. And this is essentially what Vern Miller did. And then later on, I'll show you what I did. I did some ultraviolet photography, much less sophisticated than what they did. We have a light source, a UV light source, and we shine it on the object to be photographed. Now, in this case, it's the shroud. And then we have a camera, and we take a picture of what is coming off the shroud. But it's not as simple as taking your cell phone, and snapping a picture with it. It's a little more complicated. And here is the light spectrum that we're interested in. The ultraviolet is over here. It ranges between 315 and 400 nanometers. And then visible light is 400 to 700. The UV is more energetic than the visible light. And in fact, if you were to go to smaller and smaller wavelengths, you get the X-rays and gamma rays and things like that. You get the really energetic stuff. And what we want to do is, we want to do the following. Whoops, I keep using the wrong pointer here. We're going to now take our UV photos. So we have two barrier filters, and I'll just let the animation go and then tell you what they're doing. So we have the two barrier filters, and we have the shroud here. And the reason for the barrier filters is we don't want the UV light source to be putting any visible light onto the object being photographed. We only want it to put ultraviolet. And the UV light source might have a little visible light coming from it. So we put a filter here, and then if there's a reflected UV light, we don't want the camera to pick that up. We want the camera only to pick up visible light, okay? And the higher energy light gets into the shroud, rattles around, interacts with the molecular conditions, the bonds, the contamination, and whatnot on the shroud, and then shows up as lower energy light in the visible light range, and that's what we photograph. So you have to do the photographs in a dark room, okay, in order to have this be effective. So that's the way the ultraviolet photographs work. Now here's the shroud, and you've all seen this, constant pictures. And I want to just say something before I give the results as to how STURP did this ultraviolet photography, how Vern Miller did it. They had a camera set up, and they would move the camera down the shroud. Now they didn't have lighting that was sufficient to illuminate the whole shroud, okay? So they could only illuminate roughly 1/16 of the shroud at a time. So they would take the top 1/16 up here and take a picture. Then they'd go over here, take another one, and they'd actually made 8 pictures down the top. They made 8 pictures down the bottom, and then they made pictures down the middle of the shroud. So that's not bad, I mean, provided that they were uniformly lit, but they weren't. The images that they took had what I call a hot spot in them. And if you're trying to get image intensity, that's a problem, okay? You can imagine taking a regular photo, take it at noon when the sun's out, and you've got a photo of something, then take it at dusk. Obviously, the intensity of those two images are going to be different. So if parts of the image didn't get the same intensity as other parts, it becomes impossible to compare different points on one image, okay? And that's one of the issues with the way that STURP did this. Another problem is that the original photos, I mentioned this, were actually lost. And if you look at the shroud, the body parts on the shroud show up in 2 places. So for example, the feet are here and over here, and I've got a label for the torso. So you have a torso on the frontal image and the torso on the dorsal image of the shroud, okay? So let's see what happens when they took these images. And these are the paths that they took, the red, the green, and the blue, okay? So they went along and they snapped these photos, and you would think, a priori, that there wouldn't be much of a difference in the ultraviolet intensity coming off the shroud. You know, why would, for example, the most interesting maybe is the red and the blue. The red is up top, the blue is on the bottom, and we're moving from left to right. And if you look at the burn marks, they're almost identical because of the way the cloth was probably folded when the fire took place. So you have almost identical burn marks, almost identical blood marks. They're not perfectly identical. But why would you have this big difference here? What would lead to that? That's kind of a strange result. I would have expected the intensity be much more like the blue curve for everything. And if you look at it, you say, that's interesting. The top part is asymmetric with the bottom part. The highest intensity occurs here, which is the torso area in the middle of the shroud. And then there's one other kind of subtle point, and that is that if you look at the dorsal intensities, and this would be the red curve, and this would be the feet area, or close to the feet, it'd be this point. And you look over here, and that would be this point, close to the feet. You find that the dorsal intensity is always higher than the frontal intensity, okay? And you have to compare, existing points. For example, you could compare this blue point to this blue point and whatnot. And There were some points that were missing, so the comparison couldn't be made for every single one. And the difference is about 10 and 50. So it's about a 20% difference, non-trivial. Whoops. Oh, wait a minute. Let me go back. So if I look at what is seen on the UV images, I have the following conclusions. It's highest in the midsection of the center dorsal, the green curve. It's higher on the dorsal than on the frontal, and that compares the two arrows with the feet for every point that can be compared. And it's higher on the top side, the red image, than on the bottom side, and that leads then to, what could cause these unique fluorescence properties, all right? Because you wouldn't anticipate this ahead of time. Now, before I tell you, one explanation, just recently, some data was published by Schwalbe and Pellicore, 2023, about ultraviolet fluorescence spectra. And these measurements were made by Gilbert and Gilbert, but the original data, again, was lost. We don't have it. But they went and they took the curves from Gilbert and Gilbert's paper, and they were able to recreate the data. And this is just from Gilbert and Gilbert's paper and shows you the points that they looked at. Now, the points they're not, mathematical points, but they're very small areas. Compared to 1/16 of the shroud, they're a lot smaller. And this is what you get if you take the results from Gilbert and Gilbert that have been recreated, and this is the UV intensity here of these points, and son of a gun, they vary with the point that you're looking at, all right? And they looked at clear, image, burn, and blood points. And so I should have had the blood, I guess, in red. I have it in green. These are the 3 blood points, and their intensity is lower. And these are the burn points, and they have a larger range. But what I'm interested in is the clear and the image areas, and they're shown over here. So they don't have any water stains or blood stains or burns or anything like that. And there's a variation. So that confirms what the ultraviolet photos were showing, that there is a variation. And since they don't have burns or anything else, what that is saying is that the molecular bonds in the shroud's linen change with location on the shroud, exactly what the ultraviolet photos were showing. So that leads to the interesting question, what could cause these unique fluorescence properties? And in 1989, Phillips hypothesized that if neutron irradiation arose from the body covered in the shroud, so here we have the idea that radiation is involved with the resurrection and the formation of the image, it could alter the radiocarbon dates. It would convert nitrogen to radiocarbon, make the shroud appear younger. It doesn't account for image formation, but if neutron radiation was occurring, other types of radiation could occur also at the time, again, of the resurrection. So this is a slide that's based on Bob Rucker's presentation at the 2014 Shroud Conference that was held in St. Louis. That was an interesting conference. I met several people here that went to that and then subsequently got involved with shroud research. There were 2 interesting papers for me that were given there. Bob's paper was one, and the other was given by Ray Schneider. And Ray looked at work of John Morgan that was published in 2012. And he was a geographer, and he looked at applying principal components based on analyzing satellite photos of the Earth. And when he took, and then Morgan used principal components on one ultraviolet photo, and then Schneider took his results for the first principal component, And he got this unbelievable correlation between the principal component results and the radiocarbon date. And he said, wow, look at this. And it turns out that the correlation really wasn't there, but it caught my eye, and I really felt tugged to that paper and looked at it carefully for a couple of years. The problem is that when the sun illuminates the Earth, you've got uniform lighting. But when STURP took the photos, you don't have uniform lighting. So now when you try to compare points, you have to know how much light hit the point, even though it was the radiocarbon area and they were close to one another. The other paper was Bob's paper, and he simulated what would happen if the body emitted radiation, neutrons. So his main assumption, this is taken from his website, is that thermal neutrons were emitted homogeneously from within the body and isotropically in all directions. And he carried out simulated radiocarbon dates for various parts of the shroud. And his computer program was the Monte Carlo N particle, I believe, program. And he's going to talk about that here at this conference. And this is what you get from Bob's results. This is his simulated results for the radiocarbon date. And this is the area that's closest to the radiocarbon area of the shroud that was dated. It's in the center, but it's closest to the piece that they took to radiocarbon date. And you can see it's giving results of medieval times. But most of the shroud dates to the future in his simulation. Now look at what you get if you put the UV, average fluorescence intensity, along with the position along the shroud. To me, that was a remarkable agreement between the two in terms of the shape. You get a double maxima. You get the highest values in the dorsal area. And it was like, holy smokes. So that leads to another question. Well, first, these are Bob's results, taken again from his website. The radiocarbon dating values are highest in the midsection of the dorsal. They're highest on the dorsal image, higher on the dorsal than on the frontal, and they're higher on the top side than on the bottom side. And all I have to do is replace those with fluorescence intensity, and I get the same conclusions. So could fluorescence intensity be affected by neutron radiation? Interesting question. So this is my very expensive experimental setup that I did. Cost a fortune. But I have a fluorescence flashlight, a camera, and linen that I had irradiated at UMass in Lowell, neutron reactor, and I took ultraviolet photos of the irradiated linen. And these are the results that I got. These are all the data points. And what you find out is that average fluorescence intensity indeed does increase with the amount of neutron radiation that the piece of cloth is getting. Now, this is modern linen, obviously. So I wanted to get to this slide, and I've only got one or two left, and then I'll close. But how can we non-destructively test the shroud for neutron radiation? And this isn't my idea. I've heard it from Bob and other people. But in 2002, the shroud was cleaned, and charred material from various burn sites was labeled and put into vials. Okay? Now, the charred material is just like, it's charred material. It's got nothing to do with the shroud. If you do anything to it, you're not going to detract from the shroud. So it's a non-destructive way of doing a test on the shroud. Very simple. So you can radiocarbon date the charred material. And you take different parts of the shroud and radiocarbon date the charred material. And if the radiocarbon date varies with location, then that could explain the shroud's unique fluorescence properties. Very simple test. All we have to do is convince the powers that be to do the test, which is not easy. There have been a couple of recent papers on applying AI to shroud images. What I've talked about today was published about 2 months ago in a journal called International Journal of Archaeology. If you Google that journal, you can get in. It's open access, so it's free. In addition to the UV images, I talk about what you can learn from applying the principal components to the visible light images. And it's interesting, you can get an idea as to where the three-dimensional properties come from if you do that. And in both cases, the image intensity contains the vast amount of information in both types of images. And then Otangelo Grasso is giving a talk, I thought it was tomorrow, but I think it's later today, it's at 11, on his work on recreating the image of Christ's face from the image on the shroud. So let me conclude with the following conclusions. UV fluorescence intensity of the linen increases with neutron fluence. That's what my expensive experiment showed on modern linen. After the neutron radiation, a collaborator who was here, Cesar Barter, pointed out, well, that neutron reactor also had gamma radiation. But then he told me here that he studied that further, and he's going to talk, I think, about that tomorrow. And the gamma radiation doesn't change the fluorescence spectra. So it was the neutrons from the neutron reactor that did it. Other researchers, Giulio Fanti have found that ultraviolet corona discharge and deep ultraviolet radiation can affect linen fluorescence. And Giulio has measured, he had a little bit of this, one slide yesterday, beta radiation from a shroud blood sample. So all of this is saying there's a really strong probability that radiation was involved in the formation of the image on the shroud, and all of these things are pointing the finger right towards that. Does it can prove conclusively that it was? No. But more research needs to be done, particularly if they would ever carbon date the charred material. That could be definitive. And this is one interesting question. Are there any other physical phenomena that can affect UV fluorescence of linen, and it's molecular bonding? That's what we want to know. What can change the molecular bonding of linen that's not a radiation effect? I can't think of any myself. Maybe there's something. But so with that, let me close, and I'll do a little plug. Joe put my book up. We were supposed to have, I think, book signing at some point. I don't know what happened, but I left a couple of copies of my book outside, and if anybody's interested, they're on real bargain there. I bought them at the author's discount. It was over 50%, so it's only $10 if anybody wants to get that. So thank you very much.
You can do some questions.
Sure.
Just point out who you want to ask.
Oh, okay. Let's see. Anybody have the, yes, over here?
Sure. One question. The assumption on the neutron spectrum was thermal,
Yes.
but I doubt that the reactor was all a thermal spectrum, right? You
That's
have been a wide range.
Cesar may be able to answer that. I think they ran it, were there other neutrons beside the thermal neutrons?
Yes, fast neutron also.
Yeah. And, but I think the other neutrons, they're faster, I guess. They're not going to affect the fluorescence. Is that right, Cesar?
But at the end, the fast neutron came below energy and become thermal neutron. Then if there are fast neutron, there will be also thermal neutron.
Yeah. So he's saying that both types, I think, would be there, and the fast ones probably wouldn't affect the fluorescence.
Well, what you're really getting into is transmutation versus neutron displacement damage, and that's something that's going to require more research, right, to look into.
Exactly, but you know, and I'm not a physicist, so I just paid to have them do the experiments. Bob?
Yeah, so that the neutrons would always be emitted in the very fast range in fission process. But then if it's a water-cooled reactor, they're going to be slowing down, and by vast majority of the neutrons are going to be thermal, even though they're emitted fast.
Okay. Yeah, John, over here.
Wouldn't the radiocarbon testing of of the burn shards
Right.
in the vials just predict the date of the burn itself?
No, the radiocarbon date is going to be predicting the date that the radiocarbon was formed. So in a natural process, when something dies, it stops making radiocarbon.
But wouldn't the vials itself just prove the date of the burn?
I'm not sure what you're asking. The vials were from 2002.
No, but I'm saying the chemicals, and I mean the material in there, since they're from the burn site,
Right.
wouldn't it just equal the date of the burn itself?
No, because the burn is not going to affect the radioactivity of the carbon. The radioactive carbon is just going to be in the charred material. It doesn't evaporate, it doesn't become CO2 or anything like that, and it's going to be there, and it will actually, you'll be able to date it as if it weren't burned.
Oh, okay, that's the point, okay, thank you.
When they do carbon dating, the first thing they do is.
They burn
the
it,
material.
yeah, exactly.
Okay, gotcha, okay, that was the point I missed. Thank
So
you.
I think over here was first, and then we'll go there.
How would it affect what you've done if the original pictures of the shroud that you've processed were done in sunlight, in other words, even illumination,
Yeah.
instead of the 16 stupidity
Well,
that was done?
you need the ultraviolet to get in, interact, and come out as visible light. If you do sunlight, you're putting in visible light, you're getting visible light off. I don't know what you're measuring then. In other words, it's like, I'm sorry?
Filter the sunlight coming in so that you remove everything except what you want.
I'm having trouble hearing. Can you get him the microphone? Where's Joe? I did analyze white light photos with the same methods, and you get some interesting results there. But the ultraviolet, the idea is that it goes in and excites the molecular bonds, and it excites the other stuff, the contamination. And then when it comes out, it's going to reflect what it saw. You don't know exactly, you don't get necessarily a fingerprint that says, oh, it's this or this, but you can see differences.
Well, he's talking about the sunlight. Why couldn't you just filter the sunlight? Well, a big filter where you could do the whole shroud at one time.
I suppose you could. They didn't do that. And they used ultraviolet, and whether it's strong enough where you're going to get enough ultraviolet in there, you'd have to, and the other problem is you'd have to, I guess, filter the sunlight that's coming in. Okay, that would be like filtering the fluorescence source that I had. And then you're going to have to put an ultraviolet filter on your camera so that you're not getting reflected ultraviolet from the shroud, you're just getting visible light from the shroud. But they didn't do the experiment that way. They actually used an ultraviolet source, and whether the sunlight would be strong enough, and they didn't want the shroud obviously outside in the sun, so yeah.
About 50 years ago, during the Cold War, there was a controversy over the neutron bomb, and it was called a capitalist weapon because it would kill people but would not harm structures.
Yeah.
I am now thinking, when Mary Magdalene met Jesus, he said, "Do not touch me." And I just wonder if maybe that had something to do with it.
Was he radioactive? I don't think so, but we need a theologist, a physicist that's a theologist over here.
Are you familiar with, I think it's called the quad mosaic photos that showed, supposedly showed the chemistry of the carbon dated
Yeah, I've
portion?
seen those on shroud.com.
Are those legitimately tell that there is different chemistry?
I haven't looked at those in great detail. I've had a lot of correspondence with Sam Pellicore. And Sam is a great believer that the color of the UV photos is the significant thing. And I was trying to convince him that if you look at principal components, the second and third principal component contains small color variations. okay? And that the significant thing is the intensity. And I haven't looked at the intensity of those photos just to see what it shows and see how they were illuminated. But it would be interesting to get an intensity map of those and see what it looks like. But the intensity, if you remember the Gilbert and Gilbert thing I put up, there's quite a change in the fluorescence intensity. If you look at the Schwalbe and Pellicori paper, the color coordinates don't change nearly as much. There are small changes in the color coordinates, but there are very large changes in the intensity by comparison. So I think the intensity is going to have more information than the colors, but I haven't really looked at those. It'd be interesting to do. Yeah.
I think you put up a slide of the position of the body and the shroud in the tomb.
Yeah.
From somebody else's research.
Yes, from Bob's.
Yeah. Is the relationship of the body to the dorsal to the contact and the side,
Yeah.
the picture there?
That's exactly what causes the asymmetry.
Okay, that's what I thought that.
Exactly, that you got a wall here, and if the body's emitting neutrons, and Bob is the expert on this, it's going to have a different effect banging off the wall close by versus open space over here.
I thought that was the concern. I
Yeah.
just wanted to be sure.
And
Yeah, so the results I got were affected by the neutron reflection off the limestone wall to the side and the limestone shelf below it.
Yeah, yeah.
Yeah.
That's fascinating.
How would Giulio Fanti's holy fire imagery affect the thermal factor
well, I've
in
talked to
this?
Giulio about that, and I don't know if Julio's here. Oh, there he is. He might be able to answer, but I think that there may be when the corona discharge occurs, which he believes, and he can correct me, is due to the holy fire, you're also getting neutrons generated. And so the whole thing could be generated. Is that correct? Yes. So that would explain the image, whereas just the neutrons and Bob's simulation has nothing to do with the image, which I thought was great because the image to me is impossible to explain. Whereas if you're looking just for the radiocarbon dating and you want to do the neutrons, that's an easier problem to do. And at my age, I don't need hard problems.
We only have about 1 or 2 minutes left.
Okay,
You can take another one.
sure.
With regard to your work, can you speak to whether surface contamination had any role or impact on the data?
If you look at Gilbert and Gilbert's, they specifically avoided contaminated areas. They went to the image area and they went to the clear areas. In the case of the shroud photos, there's a lot of symmetry between the top and the bottom. The burn stains are almost identical, and the blood marks are close, and you've got a pretty big area that you're averaging. So I'd be surprised if you could show that, you know, one of those was contaminated, and that's what's, I mean, you've got too much of a pattern there. It's not just, you know, you've got the red higher than the blue, you've got the green being the highest. Is it definitive? No, because what needs to be done in addition to the radiocarbon dating is they need better UV photos of the shroud where it's uniformly lit. Then we can compare apples and apples. Yeah.
So in looking at the original shroud UV photos, the serum fluoresces, one thing that kind of confounds that is the banding. If the shroud were to be rephotographed again with UV, is there a way to selectively filter out that banding?
Oh boy, I'm not a photographer, so I don't know. But all I did was take what was there, which it was great to get because when I first started, which was right after the 2014 conference, there were no UV photos available. Giulio actually gave me one from his library. I don't know if he remembers. It was like in 2018. And that's when I began to notice this hotspot thing. And then fortunately they were published. So, but yeah, if they do take more UV photos, they really need to get people that are experts in photography and to look at all these issues and then do it properly. Barry Schwartz told me that he wished that he had been involved in the UV photos with the lighting, because he was involved with the direct lighting and made sure that it was uniform. But he wasn't involved with the UV lighting. And he would have, then maybe been able to square that away. Maybe they should have focused on a smaller area instead of taking 16, maybe take 32 or something like that, so.
Okay, we better end
Okay.
here, and Tom will be outside signing books and answering any other questions you might have.
All right, thank you.
Thank you.